So now we're going to draw our attention to the double angle formula for cosine. I laid this out in the last video as cosine 2 theta equals cosine squared theta minus sine squared theta. However, because we have the presence of a cosine squared and a sine squared, we can rewrite this using Pythagorean identities. So if we were to take the Pythagorean identity, sine squared theta plus cosine squared theta equals 1, and solve it for either cosine squared or sine squared, we get the following two equations. Now that allows us to rewrite cosine squared as 1 minus sine squared. So we'd have 1 minus sine squared is 1 minus 2 sine squared theta. Okay, so that's the second version equivalent to the original double angle formula for cosine. We could do the same thing by rewriting sine squared as 1 minus cosine squared. So now we'd have cosine squared minus 1 plus cosine squared, or 2 cosine squared theta minus 1. Okay, and these three versions are all advantageous for different reasons. The nice thing about these second two versions are all equivalent, but if, for example, you only have the sine of theta and you want to get the cosine of 2 theta, you could use the second formula. You don't have to find the cosine and the sine of theta to use the first formula. And similarly, if you just know the cosine of theta and you want to get the cosine of 2 theta, you can use the third formula. You don't have to find the sine of theta. So that's one benefit to these alternative versions. There's another benefit that we end up using a lot in calculus classes. And that is, we can take these two equations, the fact that both are equal to cosine of 2 theta, and solve them for the sine squared or the cosine squared term. So for example, if we were to take the equation cosine 2 theta equals 1 minus 2 sine squared theta, and rewrite this by solving for the sine squared term. So what we could do is add the 2 sine squared to both sides, so move that to the left-hand side, and subtract the cosine of 2 theta from both sides. And then divide through by 2, we get sine squared theta equals 1 minus cosine 2 theta divided by 2. So what we've done is rewritten the sine squared of theta as something involving cosine of 2 theta, cosine to the first power. If we were to do the same thing with 2 cosine squared theta minus 1 equals cosine 2 theta. So if we use the third version of the double angle formula for cosine, we'd have 2 cosine squared theta equals cosine of 2 theta plus 1. So we'll start by adding 1 to both sides, and then we're going to divide both sides by 2. So we get cosine squared theta equals cosine of 2 theta plus 1 divided by 2. Okay, and these two formulas are what we call power reduction formulas. So this would be how we could write sine squared in terms of cosine to the first power, or cosine squared in terms of cosine to the first power. There's a third power reduction formula, which I'm not going to write here, but it's going to be for tangent. We would get the tangent squared formula by doing sine squared over cosine squared. So if we divide this term by this term, we're going to end up with 1 minus cosine 2 theta over cosine of 2 theta plus 1. Or sometimes you'll see that written as 1 plus cosine of 2 theta. All right, so let's use this power reduction formula in an example. So keep those formulas and get rid of the rest of this. So you'll notice how everything thus far has kind of built on everything else. We started out with the sum and difference formula, And the sum and difference formulas gave us the double angle formulas. The double angle formulas give us the power reduction formulas, and they will give us the half angle formulas as well. We'll get the so-called half angle formulas by taking square roots of these power reduction formulas. So really all we need to do is convince ourselves that the sum and difference formulas are true, and then we get a whole lot of other important formulas for trigonometry. And as I said, this is something that we do use a lot in calculus. If you're going on to take Math 140 and Math 141, in Math 141, we use these formulas to do integrals of trig functions if there's a sine squared or a cosine squared in the integrand. Okay, so let's suppose we wanted to simplify 2 times the sine to the 4th power of x. I'm going to use something bigger than sine squared, because if we use sine squared, we're just using the formula once, and that's kind of boring. So I'll use a sine to the 4th power. So what we're going to do is reduce the powers of this until everything is raised to the 1st power, that we don't have any sine squareds or sine to the 4ths or cosine squares or cosine to the 4ths. We're going to reduce this down to all terms being trig functions to the 1st power. In fact, they'll all be cosines to the 1st power. So the first thing we want to note is that sine to the 4th is the square of sine squared. Okay, so this is 2 times the sine squared of x squared. And that means we can apply the power reduction formula for sine squared. And replace sine squared of x by 1 minus cosine of 2x over 2. So now the thing we're taking sine squared of is x, so that's going to take the place of theta. Okay, and now we're going to just do some algebra. We have this 2, and then we're going to multiply out our numerator. So if we square our numerator using the FOIL method, that's going to be 1 minus 2 cosine 2x plus cosine squared of 2x. So one thing that you want to be aware of, if we take the cosine of 2x and we square it, we think of 2x as being like a theta. Cosine theta times cosine theta is cosine squared theta. Cosine of 2x times cosine of 2x is cosine squared of 2x. There's going to be this temptation to multiply the 2x's as well and say it's cosine squared of 4x squared. That is not the case. The thing that we're squaring is the cosine. It's the cosine function. We don't square the 2x here. So it's cosine squared of 2x. And then, so here we've multiplied out the numerator using the FOIL method, or a minus b squared is a squared minus 2ab plus b squared. And then we square our denominator, we get 4. Okay, so we have a 2 over 4. That reduces to 1/2. Now before I move on, I'm going to simplify that a little bit. I'm just going to break that fraction up, because 2 of those 3 terms are what we want. So we have a 1 over 2. We have 2 cosine 2x over 2, so we're going to have minus cosine of 2x. And then finally, plus 1/2 cosine squared of 2x. So all I've done here is taken this fraction and split it up into 3 separate terms. Okay, so the 1/2 is fine, that's reduced. Cosine of 2x is fine. Now we want to use a power reduction formula for the cosine squared term. Okay, so if we use the power reduction formula for cosine squared, this is going to be cosine, and we always double what was in the cosine squared. So if we have cosine squared theta, that becomes cosine of 2 theta. Now we have a cosine squared of 2x, that's going to double to a cosine of 4x, plus 1 divided by 2. Okay, so now we're done with our power reduction formula, so I can erase these. And now we just do a little simplification. So we have 1/2 minus cosine of 2x plus, now I'll pull the 2 out, so we're going to have 1/4 times cosine 4x plus 1, okay, or 1/2 minus cosine 2x plus 1/4 cosine 4x plus 1/4. And then finally we can combine the 1/2 plus 1/4. So that's going to become 3/4 minus cosine 2x plus 1/4 cosine 4x. And so now we've taken the power reduction formula as far as it can go. We've gotten rid of all the powers of our trig functions. Now we just have constants and cosines to the first power. Notice, because we had to use the power reduction formula twice, because we had to sign to the fourth, we end up with a 4x as our biggest multiple of x. If we had to apply it another time, if we had like a sign to the 8th, then this would be a cosine of 8x. So this number will always be equal to the power that you're reducing to start the problem. Okay, so that was an application of the power reduction formulas. In the next video, we'll take a look at the half angle formulas, which are the last set that we're going to derive from the double angle formulas.